Welcome back. I said now we'll talk about some more details on how all this fits together. You remember back in chemistry and even back in the last unit that we messed with the law of conservation of energy, okay? You remember that, the work in equals the energy out. Well, the same thing here is true with heat. The energy lost by one object is equal to the amount of energy gained by another object, okay? Energy within a system must remain constant, okay? Remember, you measured the amount of energy gained or lost with Q equals MC delta T, okay? So basically what you have is the energy gained by one is the energy lost by another. So we talked about, putting an ice cube in some hot tea, okay? Eventually, that ice cube and the tea reach the same temperature. They reach thermal equilibrium, okay? And for convention, if you want to, what we'll do is put the energy gained on the left and the energy lost on the right. Again, here's your temperature differences here, right? So you have the MC delta T of the gain side has to equal the MC delta T of the lost side, okay? Just remember, those energy changes have to all add up somehow, right? You just can't be making stuff up. So how is energy transferred? Three different types. I think, again, also you had this. You had conduction. This is direct contact. Conduction, contact, okay? If you're on a hot stove and you're boiling some water, okay? If you don't have the right types of pans or you just, whatever it is, I don't even know what those things are made of these days, but you usually, if you grab a towel, if it's all metal, right? Certain things like to conduct heat better than others, okay? Conduction, contact. Convection is the motion in a fluid. It's no different than what? You know that hot air rises, okay? So does hot water, okay? Hot air rises. The air over the equator rises, okay? Goes up into the upper atmosphere, then has to turn out a little bit, okay? The area over the poles sinks. When we get a very, very cold front, do you think it's coming off the Pacific Ocean, or do you think the original front is coming off the poles? Well, it's coming off the poles, folks, okay? That cold air is sinking. If you've ever been skiing, a lot of times after a snowstorm, you get real cold weather. Why? Because that cold weather behind a front is more dense and it sinks. Stays in those valleys. If you've ever been up to someplace like Jackson Hole, Wyoming, okay, that valley just traps cold air. I was skiing up there a long time ago and it was minus 50 degrees at night, okay? It dumped about 3 feet of snow, so the skiing was great, but jeepers, it was cold. We also have what's called radiation, which is the emission of EM waves, okay? You can think of it as, the sun heating the earth from, 150 million miles away. You can also think about it warming your hands by the fire. You don't have to put your foot in the fire to know that the fire is hot. You can just stand next to it and those EM waves will be transferred to you. So these three are very specific: conduction, convection, radiation. Okay? Conduction, molecules heat up, right? You start moving molecules. Everything is bumping into each other. Put your hands around a hot coffee cup, you go from high energy to low energy, right? Whoop. Convection, you get hot air rising, you get hot water rising, okay? It happens in the ocean a lot, right? the water around the equators is also very warm. That means that's got to go somewhere, and it moves. Well, it pushes down denser currents, colder currents down, and the warmer water stays up. Okay? It's kind of like if you've ever been fishing in the summertime in a lake, a lot of times what happens during the hottest summer? Well, fish go deeper because they like the colder water. Colder water is more dense. Radiation doesn't really require a medium to transmit it. Radiant energy travels in these electromagnetic waves. Okay? This is here is an infrared picture. There's infrared film for cameras and infrared photography. Okay? Let's try to look at some examples here, just from a mathematics point of view. You know, a 0.4 kilogram block of iron is heated from 295 to 325. How much heat had to be transferred if the iron has a specific heat of 450 joules per kilograms Kelvin? Okay? Where are you going to go? You know that delta Q is mass times the specific heat capacity times the change in temperature. Okay? What's my mass? 0.4 kg. What's my specific heat? 450 joules per kilograms Kelvin. And how much did our temperature change? 325 minus 295. Sorry, I lost my spot. Okay, remember, this is always going to be your temperature change is going to be final minus initial. Okay, it has a little bit more to do with it when we get into degrees C. You got to be careful since there's no negatives in Kelvin. I mean, 0 is 0. Multiply that across, what's that? 30. Okay. And the amount of energy lost or gained will be 5,400 joules. Okay? Just watch your units, right? What dictates what units you're going to use are usually the units in that specific heat capacity. What is the heat capacity of 1 kilogram of iron if 9,000 joules of thermal energy are required to increase the temperature by 20 degrees? Okay? Again, the same formula still applies. Okay? But what do we know? Your specific heat capacity is unknown. Your mass is 1 kg. Your delta Q is 9,000 joules. And your delta T is how much? 20 degrees C. Okay? So what would you have? What does that look like if we start plugging and chugging? It's okay to write down your knowns here, folks. I don't have a problem with that. There's a lot of things going on. So what do we have? So we have what? 9,000 joules, right? Sorry. Equals 1 kilogram times C times 20 degrees Celsius. Okay? 9,000 divided by 20 is 450 joules. Let's go to another one. I think this might be our last one. I can't remember how many I put on here. A container has 0.5 kilograms of water at 15. You put in a block of zinc at that temperature. What now is the final temperature? Again, the same formula still applies here, right? And you're going to hear me write this and say this about 8,400 times during this unit. Okay? What do we know? We got a mass is what? 0.5 kg. That's of the water. Let's keep these straight. We have a second mass of, did we have zinc? Is that what it was? Of Zn is where'd we go? 0.04. Final T, we don't know. We got the C of zinc, the C of water. Whoa, I'm running out of space. I may have to stop this and add another page so we can get some work done. Okay? So this problem is a little bit more difficult, simply because there's a lot going on mathematically. What do you know? You know that the Q gained equals the Q lost, right? So set up your MC delta T's. Okay, I want you to work this one before I do this. Okay, simply because I want you to have some experience with working on everything, right? So you got the MC delta T over here and the MC delta T over here. Okay, so which one gained? Which one lost? I want to talk just the ideas first before, and these are on the PowerPoint as well, so if you need to go back over there and look at how these are solved, that's where they're at. You know, the water starts out at 15, okay? You put in a piece of zinc at 115, okay? Who loses and who gains? Well, just think about it. Is the water temperature going to go up or going to go down? The water temperature is going to go up. So you need to do this side for the water and then this side for the zinc. Okay? I think all the math is on the PowerPoint, so check that out. Can't remember what else is here. A couple of the things that we're looking for, why, you know, in what situations would heat transfer matter? Heat transfer is all over the place, from how cold our classroom is or how warm it is, right? Everybody keeps punching the thermostat. Why? They're trying to reach equilibrium. At equilibrium, everything feels normal. Okay? What does all this mean? Where are we at? What's the big idea here? And this is kind of important as we go forward and try to figure some things out. Okay? What's the big idea? After all of this, what do you think what's going on here? Okay? What's the big idea? Well, number one, heat. Heat is the transfer of thermal energy. Okay? Due to what? Due to the temperature difference. Okay? So then next, what's temperature? Well, temperature is a measure of the average molecular kinetic energy. Okay? See how these ideas flow? Now we get into energy. We got energies neither created or destroyed. Okay? Heat energy is transferred. Okay? How? Well, you got conduction, you got convection, you got radiation. Okay? So remember, conduction is contact, convection is hot fluids rising, and radiation is through electromagnetic waves. Just remember, radiation, you just got to be in the neighborhood. Okay? You got the specific heat capacity, right? Measures how well that heat moves from one material to another. Okay? Measures how objects increase or decrease their temperature with the increase or decrease of energy. Okay? And then you have heat transfer. What happens? This is related to the conduction, convection, radiation, but what do you know? You know that the heat gained equals the heat lost. Set up your delta Q's that way, right? Makes sense? That comes down to the specific mathematical part of Q equals MC delta T. And I think you used the Q equals MC delta T last year. I sure hope you did. Makes my job a little easier. But that's our big idea here. We're talking about energy, so we can talk about heat. You know that heat's the transfer of energy due to temperature differences. Temperature differences. Temperature is a measure of the movement in molecules, okay? You know that heat energy is transferred. Each material has a specific heat capacity that's personal to that. It's an identifying trait. And then you know, from a calculations point of view, you got the heat gained equals the heat lost. Okay? I'm going to stop this one. Take a look at the PowerPoint if you can, the couple problems that are on there. I may have to put a couple of those up just to make sure. We'll see you in a